Oui, une autre fois en anglais, dommage. This is about what we do all day, which is doing FFTs. Getting the most out of your FFT. And I'm doing this from a different computer this time. So hopefully that gives us less trouble. Come in. So when we are doing FFT, the goal is to look at spectral lines where you have signals that are just slightly a little bit above the noise. Usually from sources that are really, really far away. And what I want to see is the frequency profile. And to do that, I need high sensitivity, not just in my telescope, but also in the algorithms that come after it. And I also want my frequency bins to be as sharp as possible, so that if I see something in a particular bin, I know that it's actually there, and not if a particular signal is there, it actually spread out over lots of bins. And all of this needs to be done with a low computational effort, because otherwise I cannot look at large parts of the spectrum at the same time. So this slide was actually already in, but it answers a question that Jean had earlier. So let's start with Ohm's law over here. Voltage is current times resistance. Power is actually the product of voltage and current, which means power is actually equivalent to the square of the voltage divided by the resistance. This holds at any time. And how do you measure power, whether you're doing an FFT or not? You take a sample, you square the number, and that is your power for that number, for that particular sample. Now that number, the only thing you know about it is it will be positive because it is square, so you know that it will not average out to 0. And if you have only one sample, it can be, this is like the distribution of possible power values. Our input power is 1 in whatever arbitrary unit that we're using, and there's a high chance that we see something close to 0, but it also goes well past the board over there. One sample doesn't really tell you much about the actual input power. But now if you start adding more to them, more samples, you get, this is for 2 samples, you see over here the list, for a few more and more samples, and you see at some point, for a large number of samples, your probability distribution actually starts to resemble a Gaussian again. And then you get to the point that every time that you make this, the number of samples 4 times higher, then the width of your probability distribution gets smaller by a factor of 2. So what we want to do is have a large number of samples in there, because the uncertainty from the power measurement scales with the square root of the number of samples. How do you get a large number of n? There's 2 possibilities. One of them is wait for a long time, which is not the preferred solution, of course. So what you want to do is a high bandwidth. Take many samples as you can. But on the other hand, if, for instance, you want your FFT to be done with a resolution of, say, 5 kilohertz, that means that this 5 kilohertz, you can only sample with 10 kilohertz. So you only get 10,000 samples per second. And then if you want, say, 10,000 measurements, because the square root of that would be 1% accuracy, for 10,000 samples, that will already take 1 second just to get a 1% accuracy in your power measurement in your FFT. And that is if everything works perfectly, if your FFT itself is working well. So let's get back to the basics. And this is really, again, what JM asked earlier. This is the hello world, I would like to say, of playing with GNU Radio. You have whatever signal source you have, you put it on a frequency, a sample rate, you connect an antenna, and you dump all of that in the FFT block, and you see a pretty graph with the strong radio stations and the weak radio stations, and you are FFTing the signal. Except you're not really, because this thing is sampling at the moment at 1 megahertz. This block is 1,000 samples that get turned into an FFT. And this only runs 10 times per second. So actually, you have 1,024 bins, 10 times per second, that's 10,000. That's only 1% out of your samples that you're using. And now earlier I already said you need a large number of samples, and now if you have a large number of samples but you're throwing away 99% of them, That means you have to measure 100 times longer to be able to reduce the variations in your power measurement, that you can actually tell something about the power measurement. So this is nice for when you have strong signals, when, you know, in one FFT go you can immediately see them, but as soon as you start shifting that averaging slider up, you will see things get extremely slow for any improvement. So this is not how we can do FFTs in astronomy. So we make the flow chart a little bit more complicated, and we're going to FFT all the samples. You have an FFT block in here. The FFT block wants not a regular sample, not a light blue box, but it actually wants a dark blue connector, and that is a vector. That is a ordered list of so many samples. So over here I take a block that's called stream to vector, and it simply takes 4096 samples and turns them into one block that it feeds to the FFT thing. And the output of the FFT block is 4096 frequency bins. So this number and that number needs to be related, and it also applies for me the window function with also that particular size. And we'll come back to the window function in a bit. After that, after I've done that, I now get complex numbers that are frequency bins, that are momentary samples of the power in that frequency bin. So again, I square them, I use the complex to mag squared, but I again use it on the vector. And then I use a block called integrate. And what I do is, for the first entry in that vector, I add it to the first entry in the next vector, and the next vector. So in effect, I'm summing all the samples for frequency bin 1, I'm summing all the samples for frequency bin 2, I'm summing all of the frequency samples for bin 3, all of them separately. So I still have a vector of 4096 different values. And then I put it in the vector sync. And you put your vector in there, and it gives you a nice little plot. Now the resolution in this case is, say, 20 megahertz. Divide by 496 gives me 5 kilohertz resolution. And because I'm actually integrating 10,000 of them, I have this 1% accuracy in the power estimate, which is nice. And because of the fact that I'm doing these 10,000 integration, this upgrades every 2 seconds. However, if you build this, at first it will seem not to work, because it will take maybe up to a minute before, for the first time, you will actually see your samples or your FFT. The reason for that is we need to flush the pipeline. GNU Radio, in order to be efficient with your computing resources, does everything in blocks. It makes a large block, and if it's done all the processing, it passes it to the next block. Now over here, the integrate block, we're spitting out 4000 values every 2 seconds. It takes much longer for the block to fill, so you first have to fill that whole pipeline before the next block will update. So instead we do a very dirty little hack. We just repeat the value until we actually flush. So this block, I put one vector in it, and it immediately spits out 40 of those vectors, and that is enough to trigger this one to update real time, which is much more convenient if you want to see, am I actually on the source or not? Are things working or not? The other thing is, I've included here a multiply constant, also vectorized. I'm using that to basically normalize the values, because I'm adding up 10,000 values. So if I'm adding up 10,000 values, my average will be 10,000 times as high. I could actually normalize over here, but then I do it on every sample. By doing it after the integrate block, it takes far less computational resources to do that renormalization all the way at the end, just before I throw it in there. Is that clear so far? FFT window functions. I'm almost sure that everyone here already is familiar with it. The idea is that if you don't have an FFT filter function, your FFT works perfectly if your sample rate is an integer fraction, if your unknown signal is an integer fraction of your sample rate. If it's not, horrible things happen. You get all these side lobes all over your spectrum, and you can't really tell your real signal apart from the side lobes of another signal. And what you do is, on your input data, before you put it in the FFT, you apply a weighting. So the samples at the edge of the FFT, the first and last ones, they get weighted almost to 0, and then these almost to 1. And this, if you were Fourier transform this would actually be the frequency representation of it. And what you see is that where normally you would have your first side lobe over here at 13 dB, it's now like at minus 60 dB, which is a huge improvement. There are also drawbacks of this, and that is that the peak over here has gotten wider, but it's no longer one frequency bin wide, it's now 2, 3, or 4, depending on which window you choose. And unfortunately, the better you want the suppression here to be, the wider it will be at the top, and that means that you lose frequency resolution. And that's also one of the things we said that we don't really want. You also lose sensitivity, and one of the reasons is you're doing this windowing. This is your incoming data. You're doing a windowing. This means these samples and these samples are basically still samples that I throw away, that I'm not using. And that is a loss of sensitivity, and I keep doing that, keep doing that, keep doing that. Now, you could then, in theory, start doing more FFTs. I do an FFT over this set of data, and then I shift my window by only half. I do it again, I do it again. But by shifting it by only half, I have doubled the amount of FFTs I need to do. Again, not a terribly good solution, especially because sometimes you don't want to do this by 2, but you want to do this maybe by 4 or 8, depending on the kind of window function that you're having. The ideal window function would actually be a function that gives us a perfectly square frequency bin. And if you take a boxcar, as it's called, a little box, if you Fourier transform of that, the dual of it is the sinc function. And the sinc function is sine of x divided by x. And because you cannot divide by 0, we also define that if x equals 0, then this function is actually 1. And you see it is actually nicely continuous over here at 0. Now this is a function that extends all the way into infinity, because it is almost like an uncertainty relation. The narrower the one is, the wider the other. So if I want this really narrow, I need a very wide version of that, which means it needs to extend further and further into time. You cannot do it infinitely, so you need to truncate at some point. Because you're not actually using a proper sinc function, but you're getting a truncated sinc function, that means that you'll see some ringing over here, some leakage over there in the frequency domain. So it's not perfect, but it's getting close. And the more of the time domain I have, the better my frequency window will be. And then I'm really using all the frequencies at exactly the same sensitivity. Now, making a really huge FFT is kind of inefficient, and it turns out there's better ways to do this. One of them is called a polyphase solution. The idea is that over here you have like a rotator, and every sample that comes in goes into a different fur. So I have 1, 2, 3, 4, and then it goes back to 1. It just keeps going round and round, and the number of these is as many as bins that you have. So it's not just 4, it's actually 4096, for instance. So you take this very long sinc filter that you have, and that you actually want to do a smaller number of FFTs on, and this fur filter has a particular length. So actually, if this filter has like 11 taps, and it rotates like that, that means that in fact you'll have 44 samples in here, and that actually determine the outcome of this FFT. That means I lose accuracy in the time domain. I don't actually know exactly where in this long term the particular thing happened, but I gain accuracy in the frequency domain, which in this particular application is more useful. Now, to go from a long sinc filter into all these separate fur filter is somewhat involved, but GNU Radio will actually do that for you. So there is actually a block in GNU Radio, which is the Polyphase channelizer. So the input is directly your input samples. you define, as usual, just in a single set of tabs, your low-pass filter or your sync or whatever filter you want to use. And it turns it into all these channels that are properly filtered. And all of these channels will now nicely have only that particular frequency. And the better you make this particular filter, the tighter, again, the filter window is. The only problem you here have is that this particular block gives you as many outputs as that you put in channels, which is nice if you want 8 or 10, but if you want 4096, it's going to be a very, very big flowchart, so that doesn't quite work. So what I've done here is add a stream to vector block, and then again complex to magnitude square, integrate the repeat block, and then make a graph of it. The other thing to know about all these FFT functions is that your zeroth bin is actually for frequency minus bin width to plus bin width, so it straddles the zero at both ends, and then all the bins are adjacent, and like your highest bin actually goes from half a bin width all the way to your half your sample rate, and then the other half of that bin is actually going to be your negative frequencies. So one bin is not particularly useful because it kind of straddles the frequency edge. So what you might want to do is actually, before this, put a complex magnification with a sine wave, so you can shift all the bins by just half a bin width. So every bin is an adjacent part of frequency space, and then your first bin runs from 0 to bin width instead of minus half to plus and half. So that particular implementation is at the moment not easy to do in a radio. Of course, if you can make your own blocks, you can do it. That's something that I'm still shying away from. There's another way that is almost the same way of doing it. So instead of alternating your samples quickly, you can also, if this is your incoming samples, and this is your window function, these are your samples, this is your window function, you can cut this into 4 pieces, like so. Each gets applied with a part of the window function. Then you get this. You can sum all of those, and you get this. And that might be hard to believe at first, but actually that is the same of doing an FFT with a higher resolution and this window function, and then adding 4 bins together. That would be computationally very expensive, but thanks to this polyphase transform, you can put this at the front of the FFT and use a smaller FFT. Again, we could use, for instance, a sync window, and you can see here the difference between the FFT approach, where you just where your window is as long as the input of your FFT, and then if you start using this polyphase filter bank approach, you can see you get a much steeper window with much lower side lobes. And again, the more overlaps you have, the longer the part of this sync X function that you can have, and the nicer and steeper this becomes. And of course, again, at the cost of time resolution. And this one you can actually build in GNU Radio. And, well, interesting things are happening again on the screen, but not nearly as bad as no slides showing. So there's a few lines missing now that are certainly on the slide. But anyway, over here you have your UDP source. So this is still data from the backend that I talked about earlier. You turn it into complex data, and then I use the same stream to vector, so I have 4,000 samples. And I apply part of the window function over here. At the same time, I delay them by 4096. I do another part, stream to vector, and I do another part of the window function again and again. And then there's a few missing lines here, but I'm sure you can see how they all are added together. And then there's a big missing line here. They go into the FFT block, and they go over here. And then you again do the complex to magnitude square to do a power measurement, to integrate the whole thing, repeat the thing again, so that you actually have a live display, and you put it in the Qt vector sync again. Now over here are a number of variables that actually determine, and don't worry, this will be perfectly fine to read on the slides. For instance, sync sample function, the sync function itself, the window function, which are all explained down here because they are not really visible. They get truncated in the GNU Radio boxes. So the easy one is the sync function is simply numpy.sync of the sync sample locations. The sync sample locations are simply in the time domain where you put your samples. So that's another function that simply goes from pi times 4 divided by 2 to plus divided by the number of channels. So this simply takes the range from minus pi to plus pi and divides it in the number of channels. Number of time steps. The window that is used here is actually a product of the sync function and the Hamming function, so that you taper the edges a little bit nicer, and then you don't just truncate the sync function. And this gives you the custom window function, which is 4 times as long as your FFT, and then you divide it in 4 ranges, which correspond to these multiplied constant vectors each. And that's basically all of it. And I've based this on this particular website, which is an educational resource for learning how to do radio astronomy with things like GNU Radio. And this is now the thing that we're using at the moment in the Dwingelo telescope. If we want really high sensitivity, really high accuracy in the power measurements for every bin, and then actually we don't just leave it at 2-second integration. What we do is we dump every 2-second file, or every 100-second file gets dumped to file, and then afterwards they also get integrated to do really hundreds of seconds of observation for the really, really weak sources, where the difference between your random noise level from your whole system and that little source that you're looking at might be 100%, and you can still detect it. And that's it. Thank you.
Question? So you said that you're still not using this for actual radio astronomy?
Yeah.
Okay, so do you have any idea when this will start to be used? And what gains do you expect to have in terms of performance?
Well, we're already using this.
You're already using it.
Because the flowchart I showed at the end was actually part of my previous presentation, where I was showing this Galaxy M74, and where we can just pick out the signal in say an hour of observing. Okay. So yeah, that is definitely used now. And
with respect to a normal FFT,
yeah.
What do you gain in terms of performance, of speed, or?
Oh no, you lose in speed, of course, because you're doing all these extra things. But actually, by using this approach, you're still doing only one FFT.
Yes.
You're just putting a lot of filtering in front of it, and that improves things a little bit. So there's actually 2 reasons that we're using this at the telescope. One of them is that it's nice to have sharper filters, so that you can actually relate each of those measurements to an actual amount of hydrogen signal that you have from the sky. The other is that earlier I was showing these FFTs that I was doing on the FPGA. There I'm limited to 17 kilohertz resolution, because if I want more resolution, it simply does not fit into the FPGA. And it turns out that for many of these sources, you want a little bit higher resolution. So you want to start using the FFT on the PC. And then you start getting the ability to use all these nice tricks to really get the most out of that FFT.
Okay.
Yeah.
Can you do that also in the FPGA?
In theory, I could do this in the FPGA, but given that I have first-hand experience how painful it is to develop for an FPGA and how lazy I tend to be, this is a much nicer solution, because I can just, click and drag and draw some lines, and sometimes they don't show up, and yeah.
And then the one last thing, I'm not sure maybe there's more questions.
You use a specific block to flush the pipeline.
Yeah.
And how does it compare to reducing the buffer size?
I've tried that. I've tried reducing the buffer size, and my conclusion from that was that GNU Radio was simply ignoring me. So, I mean, each block I think has like an output or an input buffer size. And of course, before I was using the repeat block, I actually tried doing that. But that does not actually change the update rate at all. And if there's people really familiar with the internals of GNU Radio, they can probably tell me why. And then I will take away this hack and do this properly. But at the moment, this solution works.
So we should have had Bastian Boven giving a talk here today, but he's passing his PhD, and he's now responsible for the scheduler of GNU Radio.
Okay.
So he will probably be able to answer why it didn't work with the buffer. So we had a decision with him. It's quite complicated how the scheduler is handled. So I would not give an explanation, but he's certainly the guy who can.
And what was the name again?
Bastian Boven.
Okay.
He's in German. He's in Trinity College.
In?
Trinity College now.
Okay.
It's a postdoc, I guess it's.
He's there.
So the guy who designed the
802.11.
Yeah.
802.11 Wi-Fi. There's a Wi-Fi implementation.
You have VM for the radio that.
Okay, yeah, I see. Yeah. Okay. And again, using the repeat block is not really terrible because all of this only happens like every 2 seconds, so it's not a huge impact. Okay.
Other questions?
No, I was just wondering, maybe in order to speed this thing up, you could put all these other filters. So there are some extensions of GNU Radio to use, like the graphic cards.
Yes.
And use accelerated structure operations.
Yes. All of that is possible and certainly interesting, but at the moment, well, this I can just click together, like I said, and this is specifically using only 5 megahertz of our spectrum, but it would be really nice, yes, where I could just take the whole spectrum, and then again, we're starting to move away from the hardware-based backend towards backends that possibly support RF knock even, and so we could do much of the heavy lifting in FPGA before we even get out of the chip. Yeah, merci.
Okay, thank you, Paul.
Merci.